Insulation performance is measured using a U value, expressed in watts per meter squared Kelvin. The lower the U value, the lower the rate of heat loss. The relationship between this heat loss rate and the thickness of insulation is not linear, however. In practice, this means that as we design to lower U values, exponentially thicker layers of insulation are required. We must also consider cold bridging, which occurs where structural elements and fixings penetrate throughout the insulation layers, and at corners and element junctions. Cold bridges reduce the effectiveness of the insulation and can lead to cold spots internally, where surface condensation and mold growth can occur. Cold bridging is also a bigger influencing factor on performance as the overall thickness increases, as the difference in heat flow between the insulation and the bridging element becomes greater. Repeating thermal bridges like stud work are accounted for by applying a correction to the U value, whilst heat loss at junctions is quantified using a psi value. Avoiding this cold bridging requires carefully designed detail at junctions and minimizing the areas where parts of the structure pass through the insulation. There are various accredited details available that can reduce the impact of these heat losses. Also, some type of constructions, such as structural insulated panels, have inherently lower thermal bridging due to their makeup. The air leakage rate of a building is measured by either pressurizing or depressurizing, and then measuring the flow of air required to maintain the difference in pressure. Normally, a pressure difference of 50 pascals is used for the test, and the result is usually measured in either air changes per hour for a passive house or meters cubed per square meter of floor area per hour for the building regulations. The same pressure test data can be used to calculate results to either standard, but the results are not usually interchangeable. It's also worth noting that air tightness here refers to unplanned air movement. Intentional ventilation openings in HVAC systems are disabled and sealed during the tests. Unplanned air movement can be driven by wind pressure acting externally, by convection within the heated envelope, or by leaks in and out of ventilation systems. The higher the rate of air leaked, the more potential there is for heated air to leak out or unheated air to leak in. Either of these will reduce the temperature in the heated areas, requiring more energy input to compensate. Air movement can also drive warm, moist air into cold spaces, creating a condensation risk. Reducing air leakage rates can have a significant effect on the overall energy performance of a building, and this becomes more pronounced as insulation levels increase. It is, after all, no use having a huge thickness of insulation in a structure if unplanned air movement allows heat to simply bypass it. Whilst good detailing can make low air leakage easier to achieve, installation and construction quality play a huge role in ensuring design targets are met. The difference in performance between a good installation and a poor one can be equivalent in energy performance terms to removing more than half of the thickness of the insulation.